Yo, yo, yo. So, yesterday we continued with the improvement of the fluid solver and implemented a few methods like this that are gonna come in handy, I think. Move data, and alter data. And then we also have swap data. And basically they are used as we store data in a texture in different channels, and we want to switch the data in the different channels. But I don't know. I've been thinking a lot lately about improving how the data is stored. Currently it's stored in two 4-channel textures. I think eventually just a 3D texture is better, way better. But I have to do some research concerning that, see like what kind of hardware one must need for that to support 3D textures. But okay, let's see. So this is where we're gonna continue now, because we have the first step is fully done here, and we do the calculations in water temporary, and then we move it to water. Although I want to see one thing here. So if I do here, yeah. So the first step moves water to water previous. Then we do the first step in water temporary. When that step is done, we move water to water previous. Oh, one second, I wonder. I think we move water temporary to water without resetting it. Pretty sure that's what we're doing. Okay. So it's back to the question yesterday: how can we clean this up and this one? We want to get to end nodes that we're always traveling in the direction of most fluid, and if we reach a point, one sec though. Yeah, so it's basically going to be we disperse water. We can either stop dispersing it in a direction because or we can stop dispersing water in a direction if the water amount from one pixel to another is 0, and it can be 0 for two reasons. In this case, or I would say the fluid amount can get to 0 because of two reasons, and it's moving upwards, and we're moving upwards, or we're moving in parallel, and we want to differentiate between those two. Pretty sure this one is moving in parallel. Actually, we want to check this one. So if we can't add fluid and we move in parallel, that's pretty much what we do here. We also want to check if the neighbor height is bigger than the minima height, because that means that we have been moving upwards, but we have moved too much upwards. So pretty much makes me wonder though. Invalid endnode's height minus m height. Is that actually what we want to do? In this case, I wonder. I think so. Yeah, pretty sure. But then we also have another case, and that's when the building grass fluid amount is less than or equal to 0. Although I wonder if we even need to check this one here. I don't think so. What's up, Airmoon? We only need to check There could be a case where we try to add fluid to a point, it already has fluid, and we try to add a smaller amount. And that's why we want to check these things. Although I don't know if that is true, however. I think we're gonna skip checking this one for now, although I am a little bit worried. But we're gonna clean this up a bit, because the thing is, okay, if we get an unvisited nodes, like if we get to this case, or if we get to this case, we pretty much handle both of them here later on, so we could just have done it here. But good morning, Wesley. Hope you're having a wonderful Thursday so far. Lowest point and highest point. Yeah, doing good, nice and chill before work later. Nice. Nice. Fuck it, let's just do it. We're gonna clean this up, we're gonna clean this up. Highest point. I'm still, let's see here. Highest point is still the highest point we reach. Maybe. I still wonder if we need highest point. Is there actually a case where we might... I think I'm gonna try without highest point first. And we'll see what we get. So we're gonna do... handle highest point. Handle unreachable point. And handle lowest. Let's see here. Handle lowest. Lowest unreachable height, highest point. What the fuck? An invalid end node. End node. Yo, what's up, Love? How are you doing? Well, I've been quite sick this week, but it's slowly starting to get better. Slowly. How about you? Long time no see. Hope everything is flowing. And yo, what's up, PG King? Same to you, same to you. Good morning, good morning. Yeah, it shouldn't be... It should be pretty straightforward. Let's see here. We do this. We have already done this. So let's take this one right now. Is it? Yeah, this one. Let's see what we get. P unvisited points first, unvisited points remove at. Yeah, now we need to do this again. Nice, yeah, good, thanks. I just moved this week, so busy. Hope the cold goes away. Appreciate it. How did the move go? And yo, PG King, I've been away the last 2 weeks. How's the project going? We haven't had that much progress the last 2 weeks. I haven't been able to work on it that much. But the few hours I have done have gone slowly forward. Thanks for asking. Was it vacation being away or work being away? Or... And Ice Rose, by the way, thank you for the follow, appreciate it. All good so far, thanks. Nice to hear. Try removing this check, done. Yeah, so I'm just gonna take this. And we're gonna put it here. And we're gonna clean it up a bit. We need P height. I think we also need M height. M height we have, that's good. It was vacation time, nice. Hope you had a wonderful vacation, man. And are we still working on the water? Yes, we are. To summarize where we're at right now. So we have a fluid solver that works. We know that it always gives stable states, roughly the stable states we want. There are room for some small improvements. And when I say we have a fluid simulation, we have from everything from the start, so the player adding water to a certain point, and we actually altering a mesh to represent the water. So we have the full flow, but it's extremely rough. So what we're doing now is we're hopefully optimizing, but cleaning up this implementation, and we're also doing it in the correct way, if that makes sense. So when we add water, we want to support, like, we want the visuals to be nice as well, and we're pretty much prepping the data to be able to visualize it in a nice way. So the initial solution didn't care about the underlying data, so the textures and such, and that's what we're introducing now as well. Yeah, we'll see how it pans out, but I'm optimistic. I think we can make it work. Yeah, fuck it, like, it has been very complicated. Not only getting the fluid simulation to work, but also making it work in such a way that we can represent it visually in a visually good way. I'm still questioning some things, but yeah, we will see. In one way or another, we're gonna make it work. One sec. Okay. Yeah, we need P height. Okay, so we get P, we get its height, or we store its height rather. I wonder... Yeah. Then I'm also questioning this quite a lot. I think we're just instantiating a lot of garbage on the stack here. So we instantiate this tuple, I think it's by reference. And then we alter this one, I guess it becomes a new one. Yeah, I don't know about that, but I think we have, yeah. Wesley, persistence and dedication, yes indeed. Yeah, with persistence and dedication, we're definitely gonna get to some result in the end, at least. Okay, so we go to all the neighbors. I also wonder about this one. We might be able to optimize this. Maybe not. But let's see, then we get the terrain patch, we get the indices wrapped, we get neighbor height, we calculate height difference, we try to spread fluid to neighbor. And spread fluid to neighbor, it always uses water temporary, okay. This we might want to change. Yes. This we don't need anymore. I'm gonna leave it here if something happens. And this one we don't need in this iteration. So algorithm step 2, calculate non-overflow fluid amount per minima. That's what we want to do. So we want to introduce 3 new costs here. And I want to name it calculate let's see here. The fuck do I want to name this? Area. First iteration finds minimas where water pool up. The second iteration we want to figure out how much water that can pool up without overflowing. Finding minimas. I think we previously named this one graph building. Maybe graph building. I think we're gonna go, basically what we want to figure out here is, or this step makes sure that we don't overflow. that's basically what this whole step is about. I think we're gonna have finding overflow. Sub overflow costs. Now finding overflow limit costs. Minimus cost. One. Okay, we calculate n height and height difference. Then we call this one, and instead of finding minimus cost base, we want to do finding overflow limit, right? And then we add it to unvisited points. Great. But there's a few more things we want to do here. This one and this one. Both of these cases we check this. So basically it's we check if the water at neighbor is 0. But I wonder about this one. Like, I have two questions about this. Is it really necessary? Add building graphs, or rather spread fluid to neighbor. Returns true if we alter the fluid value at neighbor. So either the spread is 0 or we are trying to add less water than we actually have in neighbor. As for the second case, so in the basic use case, I don't think the second case can happen, but I wonder what will happen when we make this work properly with already existing water. That's what I'm wondering. Or does this only fail when we try to add 0 water. And let's keep it like that for now. So I want to do an else here, and previously we solved this with 2 different cases. We're gonna solve both of them in here. Or yeah, I think so. If this is the case, however, we want to break. Ooh, 1 sec. Within this one, we also want to do if final point contains n. Actually, I guess we can just do remove. I want to double check that. Okay. Basically, so the first step of the algorithm finds the minimas, and then we walk from each minima. So if, and we start by walking from the minima with, let's see here, with the biggest, or yeah, with the biggest height plus water temporary. So that means that like if we walk from one minima and we get to another minima from that minima, then we want to remove the second one from the list, because that means that we don't care about that minima anymore. It gets filled by another minima, so it doesn't matter. Basically. And I just noticed one thing, however, that sucks. I think we're gonna have to do some more prep here. Or are we? No, I don't think so. Or we're gonna have to do one more prep, but it's going to be very simple. So basically, after the first step, we move all the data we have in water temporary to terrain data type water, but we just don't move it, we also add some transforms to it. So we set water temporary to be either 0 or 25, and then this is also weird. Max. Yeah, we probably don't want to max this, we probably want to add them, I would say. Yeah, I'm pretty sure. Like I wanna visually describe in a better way what's actually happening here, or to make it clearer. Yeah, I don't know if I can make it clearer right now. Then these calculations are basically here. So the first step finds the minimas in the terrain where we want water to pool up, and then we clamp the new or the water amount we add to 25. So the value is always between 0 and 255, so we pretty much add 0.1 almost, or a little bit less than 0.1. So then we know that at all of these minimas we reach, 0.1 water will be added. And the next step here, we want to figure out if we add 0.1 water or 25, will it overflow? If it will, then we don't add it. previous one. Okay, that's good. Okay, so here we have if height difference is equal to 0 between point and neighbor, and n height is bigger than m height, then we want to do something. Else if n height is less than lowest unreachable height. So then we need to introduce lowest unreachable height. Can we do, what is it, int max value? But then again, let's see. And if we get to this case, we pretty much want to do invalid endnodes add. But what do we do? Invalid endnodes order by final fluid amount. Height minus m height. So final fluid amount is equal to n height minus m height. And what I did here, like calculating final fluid amount here, that's what I want to do for this one as well eventually. So previously we went through this one a lot of, like, we finished this whole while loop, then we did some final fluid amount calculations. We might as well do these within the while loop, I think. Yo, what's up, Ahmed? My only question is highest point height, lowest unreachable height, highest point. Yeah, this one, highest point here. Is it really necessary? Highest point height minus m height. That's the highest point we can reach with fluid. Will there exist cases where highest point is bigger than, or will there exist cases where highest point height minus m height is bigger than lowest unreachable height minus m height? Probably. Yeah, we're gonna do it like this. Final fluid amount is going to be equal to, we're gonna start by making it equal to we're gonna do this. Final fluid amount is equal to m dot terrain patch terrain data get data terrain data type water. So basically we have moved water temporary to water, so we just get that value again. That is the, so when the initial phase of the algorithm finished, we put whatever water amount should be at that minima into the water channel, and we just get it back here pretty much. But I also want to do m dot terrain patch terrain data set data water temporary, and the value should be final fluid amount. Apply no. Because much like the first, so when we enter this algorithm, we do it with a fluid amount, and the first thing we do is we set the start point to contain that much fluid amount in water temporary, because during the different stages of these algorithms, water temporary will always hold its current state pretty much. So this is just to set the initial value, which we'll later work with here. And similar to this, we also need to do the same thing here, and we do it like this over here. Okay. So basically we want to calculate this and this, but we only want to do it in here. Like if we get a final fluid amount here, let's see. If this one happens, we don't want to do this, and if this one happens, we break. So yo, what's up, Andres? Yes, indeed. Yeah, so if this one happens, we want to do unvisited points clear, and we want to do break. So if this case happens, once again, this case pretty much states that we have moved the fluid upwards previously, and now it is drying. Sorry, it's drying up because we can't afford to move in parallel anymore. Which means that the water will stop at this amount. So clear unvisited points, break. And we just break. Good question. Yeah, this time around we have 2 for loops. Just have to make sure. Break in nested loop. Yeah, let's see. Oh, code 2. Go to is ugly. Oh, can I rework this one into separate methods? Andres, hello, I just wanted to mention that your tutorials are so great. Thank you, appreciate it. Hopefully I will be able to produce some more of them. Yo, what's up, Emena Pro? Long time no see. Still working on water over here. Okay, this is what I was dreading. This is the options we have. But then again, I've always wondered if we might want to visit. Nah, probably not. Did you finish Terrain? Yeah, I think it's in a... Like, we're still working on it, improving it ever so slightly, but it's in a pretty acceptable state right now. Okay, break won't work here, and I would also like to... go to... I don't want to use go to. This like this... and this has a lot of similar code. It's basically just I guess we could also... You could add a bool here. Or here, rather. But one thing, I'm not so sure we instantly want to break here. Or do we? Now there might actually be a case where we try to move to a neighbor that is parallel, and that one fails, so we get to this one, we get final fluid amount. But one sec. Nice to hear, Amena Pro. Good luck with continue creating games. If we move to one neighbor in parallel, we might dry up, but if we move to another neighbor that is downwards, we might not. Fucking hell. So I'm not so sure we want to break here. But final fluid amount here will make it so that we won't be able to get over that point the next time around. We probably want to break. But this time around, this one won't work, so... How do I want to do this instead? Jack's builds, thank you for the follow, appreciate it. What engine, brother? Unity. Fucking hell. Go to feels like the best case, but eventually I would like to have it in methods. If exit condition. What the fuck? Okay. Isn't that pretty much go to? Good morning, Kendo. I'm afraid that the majority of this and the majority of this is the same, but we have some few things that differ, and they are pretty much nested in there, which makes it to restructure it as one method. It could be done using anonymous functions and stuff like that as arguments, but it would be a mess, extremely hard to follow as well. And Kendo, how's progress? For the past couple of weeks it's been slow, haven't been working as much as I would have liked to, but you know, still moving in the right direction, I think. Or at this point, I hope we're moving in the right direction. Go to. I want to avoid go to. But, I mean, when it comes down to it, I don't know if it's in this case you could do I is equal to, you could do this as well, I suppose. Clear this one, set these to int max, which means that this one will fail, this one will fail, this one will fail. So eventually we will get out of this. But what the fuck? Or surrender to go to, I guess. The thing with this one as well, what we need to keep in mind here is by doing this, it should be okay. It should be okay. Okay, lowest unreachable height. here we just set this one, and then we do, oh yeah, we need highest point as well. That is true. Although I wonder. Lowest unreachable height. I want to try skipping this one. So lowest unreachable height, possible new fluid amount, if possible new fluid amount is less than final fluid amount. Do we need to check that? Yeah, we do. So I would like to do so instead of checking this one here, what I want to check instead is if fuck me. Yeah, we want to set the new lowest unreachable height, but then we also want to do, in one go, I want to do this. Lowest unreachable height minus m height. Although I wonder. Mm-hmm. Skip this one. We still want to do this one, I think. So we skip this one for now. We don't do this, we don't do this. This is handled. This is handled. And this is handled. So while one sec. This is handled, hopefully. Introduce fluid group, we can do without that one. Do this again. Yeah, we want to wait with this one. Okay, before we do algorithm step 2.3, I want to try and visualize algorithm step 2.1. So this one. Which might possibly crash it, but it's okay. Actually, let's see here. Basically, the only thing we care about here, or the only thing we calculate here, is this one. I wonder... Let's see if this works, first of all. Or if we get a crash. So at the end of this one we will have values in water temporary that represents let's see, finding overflow limits. Finding overflow limit. Final fluid amount. That's right. So for instance, if if we had 0.1 water here or 25 in integer value, we won't find a minima. We won't find a minima. So we won't even do this one. So we will never get step 2.1, we will just get step 2 full finished step. Yeah, so we will do step 2 prep, then we will do step 2 full, but we're gonna rename this one to final. Oh, yeah, let's just restart this. So no step 2.1. We'll just jump to final, I think. And how does the cost parameters look? Terrain fluid solver. Finding overflow limit cost base 1. Finding overflow limit cost up multiply 1. Finding overflow limit cost down multiplies 0. I think that's okay. Let's see. Okay, what do we get? Step 1 prep, step 1 find minimas, step 2 prep, step final. That's good. And let's see if we can find a minima. Height 0, height 1, 2, 1, 6, 3, 6. Yeah, so this is a minima. Okay, good to know. We get step 1 prep done, step 1 find minimas done, step 2 prep, and then we get index out of bounds. Interesting. Get terrain patch unsafe. Terrain fluid solver 125. Okay, so we get a terrain patch index increment. But we don't have a neighbor there. Wow. Okay. OB, what's up? What's up? What are you working on? Do you want me to answer that generally or specifically today? NX, PX plus I, PY plus J. The fuck? Generally. Okay, I'm working on a creature collecting game much like Tamagotchi / Viva Pinata / Sonic Chow Garden. That's pretty much what we're working on. Okay, get terrain patch unsafe fails. The reason we use it is because I thought it couldn't fail, but apparently it can in this case. Why? Whoa, one sec. Does it have to do with IJ int max value? You. I wouldn't think so. So if I is max value and j is max value, this one should fail. This. Oh, are we overflowing? We probably are. So we're overflowing, right? We set these, then we increment, then we check. Oh, that's rough. So yeah, I mean, we could just set them to 2. It's not clean, but yeah, let's see if this is the case. And one sec, just gonna get a new cup. Okay, back. Let's see if this was the case. I think it is. Water. Height 0. Okay, no errors. Step 1, prep. An OB, by the way. Thank you for the follow, appreciate it. If you enjoy Tamagotchi and Sonic Chaos Garden, by the way, you should try Viva Pinata as well. One of my favorite games, but it's quite old these days. We find minimas, we do the second prep, and then we do finding overflow limit 1. One. Then we do step final. Overflow limit 1. Does it make sense? Not so sure. Finding overflow limit cost base 1. Now we should definitely be able to walk longer, I would say. So we start here with a water temporary amount of 25, and then we walk here, we get to 21. 0. The fuck? Finding overflow limit 1. I don't... That is definitely not correct. Final fluid amount is 1. Maybe. I think the first two are very limited, and Chaos Garden in its case is a side game. That is true. Fucking enjoyed that side game more than the actual game in Sonic Adventures 2, I think. So quite curious how you extend that into a larger game. So, well, I guess the best comparison is Viva Pinata. And yeah, so in this game, you're basically going to be given a plot of land. And then you need to cultivate it and terraform it and do it into a nice garden. And depending on how you do, creatures will come and want to live in your garden. That's basically the gist of it, I think. And right now, specifically on the topic of terraforming, we're trying to implement water terraforming. So we basically want to be able to add lakes and rivers and stuff like that to the terrain. And yep, it's rough. I think what we're getting at here, I wonder if this one walks... It doesn't seem to be walking that much, actually. Water temporary 25, 21... Alter data. We should be clearing it here. So water temporary should be 0. We should be getting water temporary here as well, I think. I wonder... Yeah, okay, so I think we get to this point. Let's see here. Water temporary 15, 18, 21. Okay, I might know what's going on. Yeah, I think I do. Oh, yeah, you have Slime Rancher as well. Haven't played Slime Rancher though, so can't really compare. But I've heard many good things about it. Yeah, it's basically gonna be a sim game, but like while in Harvest Moon, or it's been years since I played Harvest Moon, but like Stardew Valley, the focus is on farming. I want to put, like, farming is, I want to minimize the farming part in this game. It's more going to be about the creatures, you know. But yes, that's pretty spot on, I would say. Slime Rancher and Harvest Moon. And yes, we have built a terrain system which is quite, I would say it's quite good. We can support real-time terraforming, and now we're trying to get the water in place. Because I want to give the player as many options as possible when it comes to making this garden theirs. So terraforming water, foliage, trees, whatever. But okay, so what I think is happening, this one stops because we try to move from this one to this one, or from this one to this one, and we fail because this one has a water value of 25. We move to this grid. This one already has a water, or this one has a water temporary of 22. We try to move to this one. This one also already has a water temporary of 22, which means that this one fails, so we get into this one, and then we check height difference. The height difference between these two is 0, so this one is true. N height, M height. The height here is bigger than the height here, so this one is also true, which means that we exit all of this. We clear unvisited points, we set I and J to 2, and yeah, we get a final fluid amount. That is, let's see, height 2. We get a final fluid amount that is N height minus M height. Actually, height 1. Yeah, okay, so it's more like we try to move from this one to this one, but it's already done. Because here we have height 1, height 1. This has height 0, N height, so 1 minus 0 is 1 final fluid amount, and that's what we get here. Finding overflow limit 1. So yes, we do need an additional check here. We need to check height difference 0. So it's not enough that this one fails. The water amount in neighbor also needs to be 0, and that is the case for this one as well, if I remember correctly. Else if 0, 0, yes. So we need to do else if. Fucking hell, do we really need to check this? Or can we alter it in some other way? Make this work. Yeah, I guess the culprit, or the, in some ways, bottleneck, is that we check every point, every grid point. We check every grid point 8 times. Which I guess we could do. Before we do all of this, we could probably add a different check, a better check. We could do I think we could do if n.terrainPatch.terrainData get data terrain data type water temporary, if this one is bigger than or equal to p.terrainPatch terrain data get data terrain data type water temporary. So if this one is true, oh yeah, we need n.x, n.y, p.x, p.y. So if this is true, we just continue. Are you trying a informed search pattern? What are your heuristics? So we pretty much have a fluid solver in place. We're just rewriting it now to use the correct data and clean it up a bit. But basically it's a 3-step algorithm, I would say. It's flood fill ish. So if we add water to a point, we first search the terrain for so-called minimas. So we find points in the terrain where water can pool up. When we have those points, we try to we do a second step through where we find how much water we can fill those minimas up without overflowing. And then the third step is just filling those minimas based on the previous gathered data. And breadth first, I'm assuming. It's pretty much, so we add, when we walk through the terrain, we add fluid to a point, and then we disperse that fluid to all of its neighbors, and we're talking 8 neighbors, not 4. And then we sort that based on fluid amount, so we always pick the neighbor with the most fluid amount, and we do that until the water has dispersed, and that's when we're done. Hope that makes sense. Yeah, if we want to go into terminology and stuff like that, I guess it could be a cascading algorithm. I have no idea. But with this check, we probably would want this check previously as well. So we pretty much check, does the neighbor already have the same amount? Or more? Or actually, I wonder if we could just check if it has any water temporary at all. I think. But spread fluid to neighbor might fail. It makes sense. Are you allowing for previous blocks to be filled from neighbors? Hopefully that should never be the case, since we're always losing water, we're never gaining water as of now. And we always, like the next point we go through, we always pick the one with the most fluid amount. Entering player could. I think this could solve it. Or once again, depends on what cost variables we use. Yo, what's up, OB? Appreciate it. Thank you for the sub. That's one way to skip the ads. Just tell me when you're back and I can answer your question more specifically. So when you create a new block, you lower the current and add an equal amount to the next block. Yes. Yes. And how much we lower the current value, or we pretty much step. So let's say that we're at a point and we want to disperse that fluid amount to its neighbors, then we do some calculations. So we check the neighbor height, and if we're moving, pretty much this is our cost function right here. So we have a base cost, so moving in we have a base cost of moving in any direction, and we increase that cost if we are moving upwards. So it's more costly to move upwards in the terrain, so we lose more fluid if we move upwards. Right now, like, it depends on these, but right now we lose as much fluid as the height difference. And then we also have in similar fashion, we have a cost of moving downwards as well. So when we move one step, we calculate the cost of moving that step, and then we take the fluid from the point minus that cost, and that is the fluid our neighbor will hold. Yo, what's up, Elias? How are you if you're moving up and down? I don't think water behaves like that. So basically, the idea is if we move downwards, we won't lose any fluid amount for that cell. If we move upwards, we will reduce the fluid amount with as much we moved in that direction. And I just have to state again that this fluid solver we're using here, like, we have constrained it in such a way that it's not really how fluid behaves in real life. Exactly, we're using it like a filling area function. We're not looking at creating a real-time, realistic fluid simulation here. We're trying to create a fluid system that is easy to use and can create unrealistic results. So basically, my go-to example of this is I want the player to be able to fill a lake on a elevated place, create a river down to another lake much lower down, and that will be a stable state in our fluid solver. In real life, it wouldn't work like that. The lake up above would drain, and the river would eventually drain as well. But that's a stable state we want to have in our game, so the end result will pretty much be as if the elevated lake had a constant influx of water and the lower lake had a constant outflux of water. So yeah, it has been interesting to find a solution that also works with all of these constraints we have. Elias GPS, what are you making? A Tamagotchi Chow Garden Viva Pinata like game, and today specifically we're working with water. Do you want to continue this function to a third or fourth area given the terrain goes deep enough? Yes. Depends on how much water we add. Like, let me show you real quick. We can do this. So let's clear this. Let's jump to terrain patch. And let's do old solution, new solution. So basically, let's run over here. And let's say that we add the max amount of water here. Hopefully this one still works, but I think so. So first of all, the algorithm finds minimas, i.e. points, which is a point in the terrain that is lower than all of its neighbors or equal to their height, and also has a neighbor that has a greater height. So all the yellow points here are minimas in the terrain. So the first step, we find all these minimas, and given the initial influx of water, we know how much water that reaches those minimas. The next step tries to figure out how much water can we add to these points without overflowing it. So we find endpoints much like this, and then the third iteration fills those areas with water, the final water amount. So if we added maximum amount of water here, most of the flow would go to here, and whatever water ends up here would flow down here. We would also get a maximum amount of water here, which will flow down here and flow down to here. And finally, this one is one of the cases I don't like this algorithm, because we get the most, like, given the initial influx here, we get the highest fluid surface here, which means that we get this result here instead of the other way around. But that is just a parameter configuration, I think. But this is pretty much how it will work. Which makes me wonder. .64, 0.31. Yeah, the initial minima find algorithm, we get a weird flow going here a bit too much, but that's just its cost parameters. I think we can solve it. We have the same issue here. 0.79. By the way, I also do game dev and programming. Nice. So the new solution is to solve that source areas are higher. Not really. What we're doing now is like this. The final result we get here is it's okay. We don't get any we get an acceptable result. We don't get any overflows. The algorithm always finish. So at this state, it's just about adjusting parameters to make the result look a little bit better. But yeah, so we have an algorithm that works in place. Now we just want to re-implement that algorithm in such a way that we can actually utilize it in the game. Because the idea is much like the character can go to a spot and dig a hole, we want the player to be able to go to a spot and start pouring water into that spot. And when the player does that, we want the algorithm to work on a separate thread, do its thing, and every time it reaches a stable state, we want to visually show that in the world by altering our water object. So basically what we're doing now is we're working the algorithm in such a way that we can actually utilize the data on the go to render it in a nice way. So the only improvements we're doing to the algorithm now is when and how we store the different stages of it, and also performance improvements. This one is my biggest ick with this one. But yeah, I think it's just a parameter setup. Have you made a separate class to store the potential water nodes into an object pool? That is not how we're gonna do it, I think. So what I'm selecting right now is the water mesh. So what we do, our fluid solver is going to store the result in a texture, and then our shader is going to do the heavy lifting, displacing the water. So yeah, the water will always exist. In most cases it will be below the terrain, and it will use the data in the texture to displace itself in such a way that it represents the fluid solver result. So adding water or removing water won't add or remove objects. It will only alter the data our shader is being fed, basically. You're editing a separate terrain map, essentially. Yes. Yeah, yes. That's what we're doing. I think it's the way to go. I have one issue with it though, that is it's going to be hard to solve, but I think we will be able to do it. So when we developed this algorithm, we needed to experiment a lot, so we implemented it initially in a pretty bad way. Mostly because we introduced a lot of objects where do we have it here? We introduced a lot of custom classes like fluid point byte and fluid group and whatnot. What we're trying to do now is we're trying to get rid of all that, and instead we work with the data directly, and we do it in such a way that we alter values. The data is stored in a texture, we alter the values in the texture without any overhead. Have you looked at wave-based algorithms? It depends on what you mean with wave-based algorithms. I've done a few water shaders in my past, and there you work a lot with waves, right? I don't remember the go-to wave algorithm. But yeah, we're eventually gonna get there, eventually. And also what I like with this solution a lot is we're gonna have, in the water shader, we're also gonna have the terrain data, the terrain height data to work with. So we're gonna be able to create nice rims. So at the edges of water, we're gonna be able to figure out if it's an edge. We're gonna be able to shade it in a nice way based on that. We're also gonna have, since we have terrain heights, we're pretty much gonna have a gradient map. So we're gonna be able to figure out flow pretty easily. Gonna be able to use flow to render the water in a nice way. But yeah, before we dive into actually visualizing the water, we need to get this fluid solver in place. And light scattering given you have normal information. Definitely. Normal information that's the big question mark. Exactly how we're going to solve it. Either calculate it on the CPU and pack it into a texture, or we're going to calculate it on the GPU, which might become too costly. We will see. Yeah, we can't really grab the normals from terrain because we might have the normals of the water and the normals of the terrain might not always sync up. We might have a upwards gradient on the terrain height, but our fluid might be still. So we might have like a plain pool of water. And mind you, this terrain system we're currently using does not use the Unity terrain implementation. We have a custom implementation for that. But like, yeah, there's gonna be a lot of problems on the road to the final product, but for every problem I have a few different paths we can take, so I think I'm pretty optimistic about it. Terrain is just a height map right now. So currently the data we store are, we have height, foliage, and then we have 2 unused. Then we have water, water previous, water temporary, timestamp. So we essentially have 32 bits just for water right now, and these are currently just to make the water, adding the water look good. So yeah, we'll see what we do about these. But yeah, just a simple height map. Actually, I think we're gonna do this. I want to be able to switch quickly between them, so we're gonna do Terraform brush is dot type is equal to terrain data type water previous, else if, and we're just gonna do old solution, new solution for now. So if our Terraform brush is water previous, we use the old solution. If it's water, we use the new solution. You can use dot product to store a 2D normal that should fit easily. Yeah, we're probably gonna need to do something like that in the end. So I guess you do calculate the normal on the CPU, and then if we had unlimited data to use, we would just store it in XYZ. But then we can make it smaller by doing dot between up and dot between tangent, I guess. And then we can recreate it from 2 float values. And if we have, we might, depending on what kind of resolution we want of the normal, we could also choose to store those 2 float values in 1 float. But yeah, we have a lot of ways to go about this. It's going to be a lot of trial and error and a lot of fighting with performance, but it's interesting. Okay, so back to this question. Is this enough? So let's say that we're at a point we want to move to a neighbor. If the neighbor has the same amount or more, we just continue. No, this won't solve it. We actually need to calculate the cost. We need to calculate the cost. Yeah. We're going to have to split this one up into two methods. One that calculates cost, much like we did previously, and one that calculates the new fluid. Fitting into 32 bits, why do you need so much performance? You have a prototype. So as for the second question, is it targeted for mobile? No. And like I just like to think about, like when we develop this, I always like to think about the different options we have if it turns out that we need to improve the performance. Like, I want to be prepared, so I usually implement it in the most costly way, do a performance check, and when I do that performance check, I want to be prepared for the case where we need to improve the performance. So I just like to think about these things. So probably by default we're going to go with calculating the normals purely on the GPU, and if that doesn't pan out, we're going to calculate it on the CPU while we do this fluid solver, and then store it as with 28 bits. If that doesn't pan out, we're going to look into if we can store it with less bits, and so on and so on. Yes, we're gonna have private int calculate spread cost to neighbor. We don't need these, we just need this one. And then spread fluid to neighbor. The only thing, let's see here, height difference, yeah, the only thing we need here is cost. And then spread fluid to neighbor P and cost. I'm Performance Hound, I get it. Do you have a prototype? No, we don't at this moment. The idea is to hopefully have a vertical slice of the terraforming part of the game done early next year. And get it out. Let people try it. But that is purely gonna be the that is only going to be the terraforming part. No, I'm developing this solo right now. And when I say we, it's me, the watchers, rubber ducks, you know. But no, it's currently a solo project. Okay, I think this looks a little bit nicer as well. And it's nice to have the cost. So we want to do the same thing down here. And we do cost. Me and the internet indeed. Although I wonder, I think I still like this, but I wonder if what we want to check here then is if else if no, actually spread fluid to neighbor. We're gonna, we don't want cost here, I don't think. We want amount, I'm pretty sure. So we want to send in amount here. We want to do this outside, I think. OB, I've often debated streaming my game dev, but I get into tangents of watching and reading other implementations. I don't think it would be interesting. I think it would be interesting. Like, don't we all get into those different tangents sometimes? And speaking, like, I've found streaming my development to make it much easier to keep consistency, keep motivated, and just produce more. I've been pretty on topic this stream. I've had streams where I've had like streams related to this water system which ended up in, the fuck did we read about? We read about yeah, we diversed and spent like a couple of hours reading about the fact that C# doesn't have overloads for byte addition and subtractions and stuff like that, and why it doesn't have it. So yeah. You can mask them with XOR in C#. Yes, that's eventually where we ended up. I, more specifically, just found it weird that, so when you do byte addition in C#, it basically casts it into integers and does the computations, so you end up with an integer. I just found it quite weird. Luva, I think your consistency is impressive. Thank you, appreciate it. Today is my 6-month sub anniversary, and and you've only skipped a few sessions in that time. Yeah, I think the most sessions was last week, I think. It's hectic during the summer, you know. A lot of things to do. But yeah, appreciate it. Yeah, just on that topic as well, it's like, it's way easier to keep being consistent in like the spring, autumn and winter, or apart from a few weeks in the winter. But summer, oh man. What's up, Norin Dev? What you do in the summer? Now it's more like I basically do this part-time, so it's just juggling it with other work, family, friends, you know. And during summer times, it's a lot. But let's see here. Spread fluid to neighbor. We want to go with I want to go with get data is essentially free, so it's okay if we do get data twice. But spread fluid to neighbor, and we're going to go with amount here. And we're going to remove this one, and we're going to do amount. There we go. It's p fluid. I wonder, am I screwing things up now? Essentially what it comes down to is we need to be able to check I think we're gonna keep it as cost there for now, and we're just gonna do n dot terrain patch, terrain data, get data, water previous, n.x, n.y. If it's equal to 0, then that's when we want to do this. Like We only want to do this or this. Yes, if the water is 0. Obvious, hopefully one day this will be more than a hobby, or more than a part-time for me at least, yeah. Definitely. That's the goal, ain't it? So yeah, I think this is how we want to do it. Like, we only find an end node if the water amount is 0. Oh yeah, I just want to try this, see what we get. Hopefully we won't get a crash. OB, if you get stuck, you can always try pseudocode or drawing it out. This often helps me to solve complex patterns. We have done so much drawing in the last couple of weeks or months. Let's see, water 0.1, add, okay, what do we get? Limit 2, that is still too little, I would say. Yeah, because I fucked up the costs here. Was it finding overflow limit? Where do we have our minima? We have it here. Okay, that's better. That's more like the previous result. Water temperature 25, 21, 11, height 26, 22, 23. Okay, that's good. Water 0.3. .5. Yeah, this is what we want to avoid. Limit 25. Or actually, I think this... might be... And this is the result. Yeah, we're not done just yet. Limit 25. So when we fill it out based on this limit, we will get to here. Okay, that's great. But actually, when we enter this step here, I don't think we want to do fluid amount here. Or actually, I mean when we enter this step right here, final fluid amount, we don't want to set it... do we want to set it to this? Yeah, I think we want to do... Basically, I'm thinking about like this in this way. So when we add water, we will be adding continuous amount of water to a point. The initial iteration calculates how this continuous flow, where it will end up. When we get to one of those points, that much water will reach that point. So for the second, and basically what we do here represents that flow. So I don't want to do 25 here, I want to do fluid amount. So when we reach a minima, we don't want to set the fluid amount there to 25 sharp, we want to set it to fluid amount. Fluid amount here is a float between 0 and 1, so we need to convert it to a byte between 0 and 255. That's done by default here, so we could just do water temporary. I think we're going to do this. Algorithm step 0 prep to do calculate fluid amount as byte, use throughout algorithm. I put this as a to-do here because unfortunately I need to run now. A bit sad. But okay, let's see here. Yeah, we will continue this tomorrow. Maybe, depending on how I feel, I might be going for a longer stream tomorrow and hopefully get this algorithm fully in place. But yeah, we will see, we will see. So as always, thank you so much for watching, everybody. Appreciate it. And have a great rest of the day. Peace.